Greetings! I want to thank Xamarin University for inviting me to deliver this webinar in which I will be synergistically combining two Xamarin technologies, UrhoSharp and Xamarin Workbooks, to interactively create 3D graphics. My name is Charles Petzold, and for the last 3 years or so I have been a proud member of the Xamarin documentation team, where I mostly write about Xamarin.Forms, and more recently the graphics technologies UrhoSharp and UrhoSharp. This webinar is brought to you by my friends at Xamarin University, whose team of mobile experts have helped thousands of developers, from newbies to tech-savvy old-timers, to deliver amazing native apps written in C#. Xamarin University subscriptions include live, interaction, mobile development training led by Xamarin experts, offered in all time zones. One-on-one sessions to get your questions answered fast. You can schedule time with Xamarin experts to review architectures, remove technical roadblocks, get mobile strategy guidance, and more. Self-guided learning is available, containing the same content as the live versions. You can proceed at your own pace to get essential Xamarin training and earn course credits towards certification. There are more than 80 live and on-demand courses broken into 8 learning tracks with constantly updated classes ranging from beginning to expert. These include access to exclusive on-demand videos from industry leaders that cover the latest mobile topics and challenges, from new platform APIs to testing and deploying on physical devices. Flexible subscription plans include a new monthly option starting at $83.25 a month, or less than $3 a day, offering unlimited access to the full course catalog, expert mobile instruction and advice, hands-on help, and more. And besides learning stuff, you have the opportunity to become a Xamarin certified developer, complete the certification track, master the rigorous coursework, demonstrate practical Xamarin mobile development expertise, and you can be designated as a top mobile developer. As you know, development is a process that encompasses much more than just banging out some code. For that reason, Microsoft offers end-to-end tools for developers to create and publish your mobile applications. On the development end is the Xamarin Platform, which lets you build native Android, iOS, Mac, and Windows applications using the world's greatest programming language, C#. The Xamarin Platform is what developers are usually referring to when discussing Xamarin, and that's certainly a big part of the story, but not all of it. The Test Cloud is a UI testing solution that allows you to write tests and deploy them with your application to our collection of devices hosted in our testing center. The Xamarin Tools enable you to build native applications written in C# for each platform. And with Hockey App, you can quickly deploy beta versions of your apps to your testers to ensure that your app is amazing before releasing it to the public. Once your application is published, we have tools to help you monitor usage, track custom events, and receive crash reports. Besides these more traditional tools, Xamarin also offers other tools to help you learn and to code, one of which, Xamarin Workbooks, I'll be demonstrating today. Before we begin, be aware that you can ask questions at any time during this webinar. Just type your query in the discussion box and our team of experts will answer them as promptly as we can. I'm going to be combining two Xamarin technologies in this webinar, starting with a brief description of these technologies and then plunging into a long demo. These two technologies are UrhoSharp and Xamarin Workbooks. UrhoSharp is a C# and .NET wrapper on the Urho 3D graphics platform. People are often curious about the name. Urho is a Finnish given name that means brave, but apparently Urho 3D was named after a brave fish named Urho. The big difference between Urho 3D and UrhoSharp is that Urho 3D has a C++ API, while UrhoSharp has a C# API, although you'll see that some of the UrhoSharp APIs still bear scars of their C++ heritage. I want to go over briefly some concepts you'll encounter during this webinar. These concepts are a subset of a full 3D education. I won't be talking about cameras or lights, for example. But you will be seeing a lot of values of vector 3 in this talk. This is the structure in UrhoSharp that represents either a point in 3D space, symbolized by the blue dot, or a vector in 3D space, symbolized by the red arrow. A vector does not reside in a particular location in 3D space. It is instead a direction and a magnitude. Sometimes vector 3 values are both points and vectors. A vector from the origin of the coordinate system to a particular point in 3D space is the same vector 3 value as that point. In 3D graphics, a position in 3D space is called a vertex, plural vertices. And the reason why is that these points are more than just positions. A vertex also often includes other information, such as a perpendicular to a surface at that point called a normal, or a particular color, or a 2D coordinate relative to a bitmap. The various multicolored dots in this slide symbolize vertices. In UrhoSharp, a collection of vertices forms a vertex buffer, and often for performance purposes, this vertex buffer might be stored in memory on the graphics processing unit for the video display. If you want to torture yourself, you can specify the vertex buffer as a void pointer, or as an array of float values, but a much better way for C# programmers is to use one of the structures defined within the vertex buffer class, as you'll see shortly. A geometry object is one or more vertex buffers. The geometry indicates how the vertices in the vertex buffer combine to form lines or triangles. A model in UrhoSharp is one or more geometries. Models can be stored in binary files with a .mdl extension and shared among multiple 3D scenes. Everything that contributes to a 3D scene in UrhoSharp is a node. These nodes are arranged in a tree structure. The camera is a node, lights are nodes, and 3D objects are nodes. What's really nice is that you can apply graphical transforms to nodes, such as translation, scaling, and rotation, and these transforms apply to child nodes as well. One of the most important types of nodes is associated with a component named static model. The static model object combines the model, which describes the geometry of an object in 3D space, with a material, which is a color or a bitmap that describes the surface of this object, in combination with lights and camera and lots of number crunching inside UrhoSharp, you get to see an actual 3D object on the screen. One of the challenges in UrhoSharp programming is organizing and consolidating data. You can combine various collections of vertices into a single vertex buffer, and multiple vertex buffers in a geometry, and multiple geometries in a model. But this static model object defines the material, the appearance of the surface of the object. So for every unique surface material in your scene, you need to go through this process from vertex buffer to geometry to model to node to static model again. In the upcoming demo, I'm going to do it 3 times. Speaking of the demo, I'm going to use the interactive programming environment called Xamarin Workbooks, which is an editor that allows you to combine text and executable code blocks and saves the documents as markdown files. But instead of me talking about workbooks, let's take a look. Here we are in Xamarin Workbooks. At the top is an empty code block ready for some C# code. You can also insert text blocks. Below the code block are several small buttons. At the right are buttons to insert a new code block or a new text block or to delete a block. At the left is a button to execute the code block. The first piece of code in this workbook denotes a reference to the Urho dynamic link library. Currently, any UrhoSharp workbook must be in a directory that contains not only urho.dll but a library file for Windows if you'll be running the workbook on Windows, or a library file for the Mac if you'll be running the workbook on a Mac as I am. The best way you can get these libraries is from an existing UrhoSharp workbook. Press the Execute button. That executes it and we get a new code block. For most of this workbook, I'm only going to need one using directive. Now normally, In an application that uses UrhoSharp, you derive a class from the application class and override several methods, and then you instantiate that class. That approach would not be sufficiently interactive for workbooks, so a special class is available instead called Simple Application. The simpleApplication.show method has an argument of type application options that you can use to specify a directory containing program resources and to do things such as specify a width and a height of the window. Execute this block, and a window appears on your screen. This is your canvas for 3D graphics. What's great about UrhoSharp and Workbooks is that it's an interactive environment. You can experiment and get immediate feedback, and that's often very helpful in 3D graphics programming. Recently, I've discovered that Urho allows you to draw lines in 3D space, and I've started to use this as an exploratory technique. However, because this is a 3D graphics environment, drawing lines isn't as easy as in 2D graphics. There is still a lot of 3D overhead to deal with that I discussed in the slides, but let's try it. To draw a straight line, the first step is to specify the starting and ending coordinates of that line in 3D space. 3D coordinates are values of type vector 3, but these coordinates need to be specified in the context of a vertex. And for that reason, we need an array not of vertex 3 values, but values of the structure named position normal that is embedded in the vertex buffer class. The vertex buffer.position normal structure has two fields named position and normal. For drawing lines, you only need to set the position field, and these two positions are the point 0, 0, 0, which is the origin of the coordinate system, and 1, 0, 0, which is 1 unit on the x-axis. When this is executed, the workbook displays the elements of the array. Generally, the workbook displays the result of the last statement executed in a code block. Let me put in a few more code blocks so we don't scroll off the bottom. For reasons you'll see shortly, I also want to define a list of these structures as well. And add axis vertices to it. Whether you're drawing lines or triangles in 3D space, the vertices must be stored in an object of type vertex buffer. This is where you specify how many vertices there are, and that they consist of a position and a normal, even though the normal is not explicitly set. The line vertices collection must also be converted to an array to become part of that vertex buffer. Although UrhoSharp is a C# wrapper, you can still see some of the underlying C++ idioms in Urho 3D in the fact that you need to specify how large this array is and what kind of elements are in it. That would not normally be required in a C# API. The next step is to make a geometry object. A geometry is one or more vertex buffers. One important piece of information here is a member of the primitive type enumeration. Line list indicates that the vertex buffer is a collection of straight lines specified with starting and ending coordinates. A model is one or more geometries. This model has only one geometry, which is the geometry just created. The bounding box is required, although the actual values aren't very important. A 3D scene in Urho is organized into a tree of nodes. The simple application object created earlier creates several nodes, including a light node and a camera node, and also a node accessible through a property named root node. I'd like to create a subnode of that root node named main node. For all the visuals I'll be creating. That code looks fairly innocent, but it has a problem. In a workbook, code cells can be re-executed. And if this one is re-executed, it will add another node to root node. For this reason, in a workbook, any code that adds a node should be preceded in the same code block with code that removes the node. Fortunately, if a node named main node does not exist, getChild returns null, and removeChild just ignores a null argument. Now let's create a subnode of main node called lines node. Named that because this node will contain all the lines that I'll be drawing. The code begins with a statement that removes lines node from main node. Attached to this node is a component of type static model that references the model object just created. Also specified on the static model component is a material object. A material describes how the line will be colored. In this case, black. The unlit technique means that it won't be affected by light, and it will be anti-aliased. These are good material properties when drawing lines. And when this code block is executed, at long last, a black line appears in the window over at the right, from the point 000 to the point 100. Of course, at this point, it's not quite clear which point corresponds to which end of the line. Yes, that is a lot of code for a single line. But now that we have this code, we can go back to the axis vertices array and expand on it a little bit. For example, let's add another pair of vertices for a y-axis. From the point 000 to the point 010. When this block is re-executed, Workbooks also executes all the code blocks that follow this one, so that everything is updated with this new array. With these two lines in place, we can deduce that the origin is the point in the center of the window, where the two lines meet. Positive x values increase to the right, and positive y values increase going up. We also see what it means for a line to be 1 unit in length. In 2D graphics, often a unit of 1 is 1 pixel or something close to it. These coordinates of 1 are considerably larger. The size is actually relative to the height of the window and how the camera is positioned relative to the graphics. Now let's add a z-axis. From 000 to the point 001. Re-execute, and nothing. The problem is that positive values of z go into the screen, conceptually speaking, and the z-axis is now hidden behind the y-axis. If we change this 1 to -1 and re-execute, we can see it, but it doesn't really look like 3D. The camera created by simple application is a little elevated above the origin, but it is smack in the horizontal center. I could start messing around with the camera, but I promised myself I wouldn't do that for this presentation. Now I'd like to draw a circle. I want to center the circle on the origin with y coordinates of 0, so that the circle will reside on the plane formed by the x and z axes, called the xz plane. Let's start accumulating data to do that. Using capital letters for a constant, I'm going to divide the circle into 20 divisions for now. That's arbitrary. And I'm going to store the results in a collection called radii. The angle is incremented from 0 to 2 pi radians. X is the cosine and z is the sine. Notice that I is incremented from 0 to less than or equal to divisions, so that the last element in the collection is the same as the first. This is often convenient when later indexing this array. Are these points or are they vectors? Well, they're both. They're points on the circumference of a circle with a radius of 1, but they're also vectors from the origin to this circumference. Now I need another collection of vertex buffer dot position normal values. This is a collection of 20 pairs of points for 20 lines. Each line begins at the origin, the point 0, 0, 0, and extends out in a radius of 1 to the radii value. Now, add that collection to line vertices. Now I have both axes vertices and radii vertices in this line vertices collection. So if I re-execute this code block, I get the lines extending out from the origin. For future reference, we should try to keep in mind where these indices begin when I is 0 and what direction they're going in. You can figure it out from the math, but an easy way to see that is to display only half of them by dividing divisions by 2 in this loop, and then by a quarter. And now we see that the indices start at the far right on the positive x-axis, and they go counterclockwise from our perspective, looking at this from above the origin. Let me change divisions back. Suppose I want to draw an actual circle with a radius of 2. I begin by defining a collection of points based on the radii calculated earlier and this constant radius value. Notice that the radius value is simply multiplied by the vector 3 value stored in radii. This code treats the members of the radii collection as vectors, so multiplying by a number multiplies the 3 x, y, z coordinates by that number. Also notice again that I goes to less than or equal to divisions, so the last value is the same as the first. Now define another collection of vertex buffer dot position normal structures. These pairs of points will go from one member of the circle points collection to the next. And here is where having one more element in circle points is beneficial, because indexing with I plus 1 is okay. Even at the end of the loop, it's still a valid index. Now add that to the line vertices collection. Re-execute. And there it is. But you can see right off that it isn't really a circle. It's a 20-sided polygon. That's called an icosagon if you want to get technical about it. 3D graphics programming is not about curved lines and curved surfaces. Everything in 3D is straight and flat, and any curvature that you might eventually see is merely an illusion. To see a circle rather than an icosagon, let's go back and change the divisions constant from 20 to, let's say, 1000. Re-execute. And we get a Kaliagon, which became famous in 17th century philosophy for illustrating the difference between what we can imagine in our minds intellectually versus what we can imagine visually. But let's go back to 20 for now. In making this circle, do I have a long-term goal? Yes, I do. I want to construct a circular two-lane highway where this circle is approximately the dividing line between the two lanes. The road will be built around this circle. In the process, I'm going to accumulate several more collections of points and vectors. You really can't have too many of these collections because they turn out to be useful later on. For example, having a collection of vectors that are tangent to this circle might be useful. Let's put it right there. and use the modulo operator to avoid over-indexing the circle points collection. Let me also define another collection of vectors called parallels. These vectors are so called because they will be parallel to the surface of the road. How wide is this road? The radius of the circle is 2, so let's make the width of the road half that. I want two collections of points here, one representing the inner edge of the road and the other the outer edge of the road. These points are based on the circle points, but offset with the parallels vector by half the width of the road. Let's visualize these new points with another collection of vertex buffer.position normal values called width vertices. These are lines that extend from the inner points to the corresponding outer points. And add these vertices to the line vertices collection. Re-execute, and there they are. Let's get rid of the axes and the radii. It's not necessary to see them anymore when the surface of the road is coming into view. I also want a collection of vectors that are perpendicular to the road, that is perpendicular to the parallels. Now, in 3 dimensions, there are an infinite number of lines perpendicular to another line at a particular point, so we have to be a little more precise. These perpendiculars should also be perpendicular to the tangents of the circle. Now, fortunately, there is something that calculates a vector that is perpendicular to 2 other vectors. It's called the vector cross product. The normalize method makes the vector have a length of 1. This comes in handy when you're multiplying a vector by a value to make a line. So, this road has a width, but it's also going to have a depth. Like the width, the depth is defined based on the radius. 4 collections are needed to accumulate the points that define the edges of this road. The previous inner and outer points are now expanded for the upper surface and the lower surface. These are calculated based on the previously defined inner points and outer points, modified by half the depth times the perpendiculars. To see these, let's have another collection of vertex buffer.position normal values. The first pair represents the depth on the outside of the road. The second pair is the depth on the inside of the road. Let's add it to the line vertices collection. Re-execute. And now the solidity of the racetrack should be becoming apparent. Perhaps these lines are even like a little reminiscent of steer girders to support the racetrack. And now, at long last, we are ready to switch from 3D lines to 3D surfaces. all the points have been accumulated that are required to construct the surfaces of this little highway. In 3D programming, surfaces are defined by a network of triangles, or a lattice of triangles, or a mesh of triangles, or a tessellation of triangles. Whatever word you want to use for lots of triangles that fit together to approximate a surface. Triangles are good because they're the simplest three-dimensional objects. Triangles have only 3 points and they're always flat. So let's begin by constructing triangles on the outer edge of this track. Every group of 4 points, such as these 4 points right here, need to be connected with 2 adjacent triangles. When you define these triangles, the 3 points need to be specified in a clockwise direction from the perspective of the front of the triangle, the side that is visible to the viewer. For example, from this point on the lower edge to this point on the upper edge to this point at the right. Let's go down to the bottom of this workbook, add a few more code blocks so we don't scroll off the bottom. And let's make a collection of vertex buffer.position normal values again. And set up a loop to add 3 points of a triangle just as I've described. Three vertices define a triangle. Now, if you recall early on when I was drawing lines, I needed to construct a vertex buffer and then a geometry and then a model and then a node just to see the lines. That needs to happen again, a second time for these triangles. And you'll see some differences in the definitions of these objects. First, a vertex buffer. The only difference between this and the first is the shadowed property, which involves how these are handled in memory. And now, another geometry object. And the big difference here is the primitive type that you'll see shortly. For the lines, this was line list, which meant that every pair of vertices defined a straight line. This is now triangle list, which means that every 3 vertices define a triangle. And a new model. And a new node. This node gets a model that is the model just created. And a rather simpler material, which is just the color gray. Execute this. And there it is. As you can see, we only defined half the triangles for the outer edge, and they're not visible from behind. Let's go back and add 3 more vertices for the other set of triangles. These now need to go from a lower point to the upper next point and down to the bottom. Execute again, and we're good. Now we should be able to define the inner edge as well. just by copying this block of code for the outer edge and changing outer to inner. Let's try it. Change the comment as well. This is where you really want some search and replace in workbooks. It's not there yet, but it's easy enough to do it manually. Re-execute. And no, this didn't quite work as expected. We can see part of the inner edge, but from the wrong direction. The problem is that triangles must be defined in a clockwise direction from the perspective of where they are visible. It's possible to fix the inner edge triangles very easily by just swapping two of the vertices in each triangle. That's simply a cut and paste job. Take the third vertex in the first triangle, cut it, and paste it in as the second. And the third vertex of the last triangle, cut it, and paste it in as the second. And now it looks correct. With these edges, the thing almost appears to have a 3D shape. The mind really wants to see 3D objects. However, there's still something a little wrong with this. The simple application object created early in this workbook defines a light source, which should illuminate objects differently depending on how they're angled in relation to the light, which means that the outer and inner edges of the road shouldn't be entirely the same shade of gray. They should be shaded a bit to indicate different reflection of light. The problem is that we haven't told UrhoSharp how these surfaces are angled to the light source. And that's really not something it can figure out on its own in a generalized way. We need to tell it. And that's why these collections that we've been accumulating are called vertexBuffer.positionNormal. The normal is a vector that is perpendicular to the surface for the purpose of computing how much illumination the surface gets. We need to go through this list and add normal vectors. Do we have something stored in one of our collections that indicates a vector that is perpendicular to this outer edge surface? I hope so. Yes, it's the parallels vector. So let's add a normal to the first one. And we can copy this and add it to the others, changing the index to i+1 when necessary. And for the inner edge, wait a minute. Is it the same for the inner edge? Not exactly. It should actually go in the opposite direction, so the normal is negative parallels. Let me copy this one now and continue. i+1. That's the same. That's the same. This should be i+1. And that's the same, but i+1. Now watch closely. When I re-execute, the change is going to be subtle. Subtle indeed, but now the shading is a little more realistic. We also need a surface on the top of this road, and I'm also going to put one on the bottom. And for that, I'd like to cover the surface with a bitmap, which in 3D programming is often called a texture. Back when the simple application object was created, a directory was specified named data. Let's take a look at that. Bring up Finder. Here's the directory in which our workbook is being stored. There's a data directory and a subdirectory named textures, and there is a ping file. That's what I want to use for the top surface. It looks like a road, right? With the yellow dividing line in the middle. For the top part of this road, clockwise triangles can go from the outer edge here to the inner edge and the next inner edge, and from the outer edge to the next inner edge and the next outer edge. So let's go. Let's go down the bottom here. Let me put in a few more code blocks so I don't scroll off the bottom. And because we're using a different material, we have to go through the whole process for a third time of constructing a vertex buffer. And for this vertex buffer, I'm not going to mess around. I'm going to do the whole upper surface with 2 triangles each. And the first starts at the outer upper and with a perpendiculars, that's the normal, to the inner upper, to the inner upper of the next index over, and the second triangle starts at the outer upper point goes to the inner upper point of the next one over and back to the outer upper. Okay. And as you'll recall, we need a vertex buffer for that. This is much the same as the previous one. And that vertex buffer is referenced in a geometry. And that geometry is referenced in a model. And now the node is created. The node references the model that we've just created, but also sets the material to a material object created from the external ping file. Execute this, and it's a mess. What happened? Well, Urho needs more information. It needs to know exactly how the bitmap I've specified should be aligned with the various vertices that define the surface of this road. Let's look at the bitmap again. We're going to be referencing this bitmap using what are called texture coordinates. Texture coordinates are two-dimensional x and y coordinates relative to the image itself. The upper left corner is the coordinate 0, 0. The upper right is 1, 0. The lower left is 0, 1, and the lower right is 1, 1. So, each vertex of this surface needs a position, a normal, and a texture coordinate. Yet, the structure that I've selected only allows positions and normals. I need a different structure. Rather than vertex buffer dot position normal, I want vertex buffer dot position normal color text coord. And I'm going to need to copy this and stick it on the end of each of these. Also, since this has a C++ underpinning, I'm also going to need to fix this, where I set the size of the vertex buffer, because it's not only a position and a normal now, it's also a position and a normal and a color and a text coordinate. Now, this structure allows specifying different colors with each vertex. I'm not going to be using that. I'm only going to be using the texture coordinate. What should the texture coordinates be? Let's take a look at the bitmap again. Vertices at the outer rim of the track can correspond to texture coordinates at the top of the bitmap, where y is 0. Vertices on the inner rim of the track can correspond to the bottom of the bitmap, where I is 1. But this bitmap is much wider than it needs to be because the image is the same for every x coordinate. This bitmap could really be just 1 pixel wide, which means that all the x coordinates could be set to 0. So let's go back to the code and insert a texture coordinate here, which is the upper left-hand corner. Now, let's copy and paste that and adjust it when necessary. X is always 0, but y is 0 for the outer edge and 1 for the inner edge. Outer is 0, inner is 1, outer is 0. And now, when we re-execute, and we get something that looks like a railroad. Let's do the same thing on the bottom surface. At this point, we can just copy all these. All the two triangles for the upper surface. Copy. Let's make some space here. And paste. And now all we need to do is change upper to lower. Upper here, lower. Copy that. Upper to lower. 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 And make all the normals negative, because they should be pointing in the opposite direction. Negative, 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 negative. And swap 2 of the triangle vertices. Cut that, paste it in there. Cut the third one, paste it in there. And re-execute, even though we can't see that lower surface quite yet. However, what we can see are those little perpendicular lines bleeding through the edges. So let's remove them. Let's go uptown, try to find that code block. And there it is. Comment out that and that one. What I also want to do is change this from an icosagon to something that better resembles a circle. So up where divisions is first set to 20, right there. Change that to 100. Now recalculate, and now the road is nice and smooth and perfectly flat. Well, maybe a little too flat. Now, earlier I did something that might have seemed a little superfluous. I defined an array of vectors named parallels. Right there. These parallels are supposed to be parallel to the surface of the road. But the vectors were set to exactly the same values as the radii vectors. I did this because everything that follows is based on these parallel vectors. And if I actually calculate the parallels vectors somewhat differently, then the road needn't be as flat as it is. And here's where you can start having fun with math and graphics transforms, and usually sines and cosines get involved because they make nice flowing patterns. For example, let me comment out this definition of parallel and calculate a tilt value that swings back and forth as we go around the track. And then use that to calculate a rotation transform that I can then apply to the radii vectors to calculate the parallels. Recalculate. And we get a road that tilts back and forth as it goes around. We could even make a couple of loops in the road. Recalculate this. And there it is. That's one loop. Here's two loops. And here's a loop and a half. And here is half a loop. What is that? Well, that is what is commonly called a Mobius strip, named after 19th century German mathematician August Ferdinand Mobius. What used to be the top surface and the bottom surface have joined into one continuous surface. And what used to be the inner edge and the outer edge have now joined into one continuous edge. Now, because of the way these coordinates were calculated, the center of the road, the yellow dividing line, has remained pretty much a circle on the XZ plane that is centered around the origin of the coordinate system. Look close, and the center line might look a little ripply. That's a flaw in my code. I could fix it by doubling the number of triangles and having edges of the triangles correspond to the center, but I'm not going to do that. But now that we've created this Mobius racetrack, wouldn't it be fun to see a couple of cars drive around it? That can be done. One of the ways I prepared for this webinar is by downloading some 3D models from the new Microsoft curated website, remix3d.com. This website is intended to be used with the new Paint 3D and 3D Builder apps included in the Windows 10 Creators Edition. The native format of these models seems to be .3mf files, which stands for 3D Manufacturing Format. It's a zip file that includes an XML description of the various geometry data and PNG files for the textures. UrhoSharp can't use these files directly, but you can use Paint 3D and 3D Builder to convert to other formats, and then use the UrhoSharp Asset Importer utility to convert to an XML file that contains data to create a UrhoSharp node that references external binary model files, XML material files, and PNG files for the texture. Let me bring up Finder again. Here's the road surface. But you can also see there's a blue racer directory, and there's a node.xml file, and materials and models and textures. The textures are ping files, the models are .mdl files, those are binary, and the materials are XML files like the node. Once you have this in your UrhoSharp code, all you need do is load in the node.xml file for a particular node, and everything else comes with it. Let's go down to the bottom of this thing now and add a few more code blocks so I don't run off the end. I want to create 3 nodes for the blue racer. First, a child of main node called car1 node. A child of that node called car1 child node. And a child of that named car1 definition node. This third node is the one that is created from the loaded XML file. Just like that, load XML. Execute. Whoa! The car's a little big. And it's kind of merged in with the road, which seems to be plowing through the windshield and the front seats. This is a good lesson. 3D coordinates are relative coordinates. They don't mean anything by themselves. But within a 3D scene, they must be consistent. Obviously, the person who designed this car didn't know that it was going to be driven on a road with a lane that is only 1 unit wide. Actually, this car was originally much, much larger. I modified the node.xml file to make it this size. So let's apply a scaling factor to car1 child node to bring it down to a proper size. Just make it 10%, and that looks like the right size. Now that's the only thing I'm going to do to car1 child node. All other manipulation of this car will be applied to car1 node. As you can see, the car seems to be sitting on the XY plane, and that is true. Turns out that if you examine this model, you'll discover that the 0, 0, 0 point is aligned with the bottom of the tires and is approximately in the center of the car, which is convenient. I want to animate this car so it drives around the Mobius strip speedway. There are several ways to animate something in UrhoSharp. For common types of animation, such as moving an object in 3D space or rotating it around an axis, there is a run actions method of node that is very handy. You'll be seeing an example of that towards the end of this webinar. But we're going to need something a little more complex. The car needs to be moved around on the racetrack and at the same time rotated and tilted in various directions as the road goes around in a circle and flips over. For a job like this, a good approach is to attach a handler to the update event of the application class. That handler has a parameter of type update event args. This method is called frequently as your program is running. Update event args has a property named timestep, which is the time in seconds since the last time the handler was called. So generally, you'll define a variable external to the method named t for time. Also, a constant revolutions per second value is handy. Inside the method, increase t by the time step value multiplied by the revolutions per second. So t increases by 1 every revolution. And then using the modulo operator, crop off the integer part so it's only a fraction ranging from 0 to 1 as the car goes around the track. Now I also want another method prior to this named getCarPosition. This method takes arguments of t and a couple of booleans indicating if the method should calculate the position for the top of the track or the bottom of the track or positioned in the outside lane or the inside lane. Those are the 4 possibilities. And it returns a vector 3 indicating the position of the car. Now this will not be sufficient to make the car seem to drive around the track, but it is a start. So the parameter t ranges from 0 to 1 for the car going 1 cycle around the track. we can convert that into an index. Now that's not really an index because it's floating point, but then I can calculate two integer indices, I1 and I2, that surround index. These are the indices we can use to interpolate. Let's first use that isUpper parameter to get two collections of points called outer points and inner points. And then interpolate between a pair of outer points and inner points to get an outer point and inner point corresponding to the position of the car. Finally, interpolate between outer point and inner point to get the center of the outer lane or the inner lane. That will be the position of the bottom center of the car as it moves around the track. Back in update car position, call get car position to get the position of the car and set that to the position property of car1 node. Now let's attach this handler to the update event of the application object. It looks simple, but there's a problem. Code blocks in workbooks can be called multiple times, and we don't want this handler being added to the update event each time the block is executed. Prior to the handler being set, the previous handler needs to be removed. However, you can't remove it simply with some C# code that detaches the handler, because each time the previous code block is re-executed, there's a new instance of the update car position handler being created, and the detaching code might not remove the right one. So some brute force code is required involving reflection. That simply strips all handlers from the update event. Now we're ready for the animation. Let's execute this block. And the center of the car is following the track, kind of. But the car is remaining in the same orientation, and obviously that's not correct. And you can see that nothing prevents the car and the road from occupying the same space. Also, I've neglected to take account of the Mobius strip. After the value of t is cycled once through from 0 to 1, the car jumps back to the beginning. Let's take care of that problem first. And I want to stop this animation so it's not too distracting. In the update car position method, I really want t to go from 0 to 2 because it needs to go twice around the track. This code that I have here is only good for t less than 1. Otherwise, let me copy this code first. And subtract 1 from t, change this to false, and false, because when it starts on the upper part, on the outside, for the second time through, it's going to be on the inner lane on the downside. Let's just check to see if this is working. It goes once around, and now from what we can see, it's on the bottom part, and now it comes back to the beginning. So, looks like we're good. Now all we need to do is fix the orientation of the car. The get car position method needs to calculate 3 more vectors. Let's call them forward, outer, and perpendicular. These 3 vectors will be orthogonal, that is, at right angles to each other. The first vector is always parallel to the surface of the road and points in the forward direction of the road in increasing index numbers. The outer vector is also always parallel to the surface of the road, but points to the outside of the racetrack. It's at right angles to the forward vector. That can be calculated by subtracting the inner point from the outer point and normalizing. The perpendicular vector is perpendicular to the road, and that can be calculated by interpolating between two members of the perpendiculars collection. And since these three vectors should be orthogonal to each other, the forward vector can be calculated using the cross product. Now that we have three vectors describing the orientation of the road at any point, what on earth do we do with them? Well, it turns out that the node class has a method named setTransform that allows you to apply a matrix transform to the node and hence to the car. This matrix is a 3x4 matrix, 4 rows but only 3 cells in each row, which means that this transform is only capable of scaling, rotation, skewing, and translation. You can't do perspective or taper transforms with it, but that's okay. Now it turns out that the 4 vector 3 values calculated by this method can go pretty much directly into the 4 rows of a 3x4 matrix. This is a common procedure, which is why the matrix 3x4 structure has a constructor that takes 4 vector 3 values for the 4 rows of the matrix. Unfortunately, that constructor has a little bug in it, so I have to fake it with a method that I'll insert right now called makeMatrix. Otherwise, we're ready to call that makeMatrix method. Let's add 3 vector 3 definitions to update car position, forward, outer, and perpendicular, and add those arguments to the call of get car position there, and for the second one. And call makeMatrix here. Look at the orientation of the car within the 3D coordinate system. Increasing values of x are to the right, which is towards the front of the car. So that x-axis must be transformed to forward, and the forward vector is the first row of the matrix. Increasing values of y go up, that is, through the driver's side door. That vertical axis in the car must be transformed to the negative of the outer vector. Increasing values of z go into the screen. Those are in the direction of the bottom of the car. Those must be transformed to the negative of the perpendicular. Finally, the fourth row is the position. Similarly, for the second part of the Mobius strip. Except that the signs for outer and perpendicular must be flipped, because with the Mobius strip connection, outer becomes negative when it switches from the outside of the track to the inside, and perpendicular is negative as well because the car is now on the bottom. Now, instead of setting position, set the transform here and here. And let's re-enable this animation. And now the car, as far as we can see, is being rotated properly in accordance with the tilt of the road. If you look close, it's not perfect. Keep in mind that the car is being positioned based on a point in the center bottom of the car. So sometimes the tires are a little above the road and sometimes a little too low in the road. But still, it's not too shabby, considering the relative simplicity of the code. So, you know what would be even better than just this one car? Having a second car. So, right after this first one's loaded in, let's make another code block and load a second one in. This is supposedly a Rolls-Royce. Again, 3 nodes. One that we can manipulate with a transform, a second that we can manipulate with a scale transform, just a scale transform, and the third that actually contains a definition loaded from the XML file. And execute that, and of course it's big again. It's actually pointed in a different direction than the blue racer. But once again, we can make another code block to set a scaling factor. And now it's about the right size. And all we need to do is add some code to update car position. This needs 1 minus t to go backwards, and it's starting on the bottom of the Mobius strip. The second part needs 2 minus t to go backwards and sets outer and perpendicular to the negatives of the other call. Re-execute this, and they're off. One last animation. This is going to apply to the whole shebang that we've been doing. Add an action to the runActions method of main node. This is going to repeat forever, every second, rotating by 15 degrees around the y-axis. However, to avoid multiple identical objects being added to runActions, begin by removing all previous actions. Let's execute this. And now the Mobius strip itself is rotating around the y-axis. We can enlarge this to fill the screen, make it a little bigger with the mouse, move it up a little, and the rotation of the Mobius strip around the y-axis seems to morph it, which is an interesting effect. But despite the Mobius strip, as the 2 cars drive around it, they always keep to the rightmost lane. They pass each other twice in each double cycle, while passing each other on opposite sides twice more. Now, I know you want to watch this for the next hour or so, but I really need to go back to the slides, because I need to recommend to you that you get started with Xamarin University today. You can sign up from the Visual Studio Marketplace, which offers monthly payment options and the ability to use your Azure subscription. Starting at just $83.25 a month, less than $3 a day, you receive unlimited access to constantly updated curriculum, ranging from topics such as C# for beginners to classes covering the latest in navigation styles and controls for Android and iOS. A Xamarin University trial includes access to self-guided learning to adapt to your own pace, lightning lectures and guest lectures covering the latest technology, and 2 live expert-led introductory courses that count towards your Xamarin Mobile Developer certification. And if you want more information about UrhoSharp and Xamarin Workbooks, check out the guides, API documentations, and sample code on the developer.xamarin.com website. In particular, if you want your own copy of the cars driving around the Mobius strip highway, go to the Workbooks page, scroll down into the UrhoSharp section, and it's the one entitled Mobius Strip Speedway. Because it's a workbook, there are plenty of text explanations within the workbook that go into more detail about techniques that might have gone by a little too quickly in this webinar. Thank you so much, and if you have any more questions, please continue to ask them. All right, file, stop recording.